Hello, hi everyone. So Xuanying, are you there? Can I start now, or do I need to wait for something?
Oh, yes, you can just start.
Okay, thank you. Thanks, Xuanying. Okay, good morning, everyone. My name is Yuxia Hu. I'm a professor in geotechnical engineering in the University of Western Australia. Very nice to see all of you join online. I would like to make this session, so I'm given the time from 9 to 10:30. I just want to make sure that you are there, and if you're, you are interested in find out what I'm going to talk about. I have asked Xuanying to leave the chat on. So I suppose most of you have attended the last few sessions by Professor Dong Wang. So if you have, can you just tap on the chat for 1 or 2 words about, what you remembered over the last few sessions? If you haven't, if you did not attend those sessions, just type N for no. So yeah, so everyone, if you can just type 1 or 2 words in the chat, so I can have a quick look to say what you remembered from the last few sessions, if you can. Can you find the chat on your screen? Can you type anything in on whatever you remember? You can type Chinese or English. I prefer English so you can practice, but if you want to type Chinese, that's fine. I can read. Anyone? I haven't seen anything on the chat. Oh, are you there? Or you just turn it on and left the screen? Come on, show me something. PPT, spudcan, geohazard. Great. Excellent. Anyone else? I got 1 response here. We have 36 on the screen. And I would like to see a few more, if possible. You can repeat what the others have typed in, and if you think you remember those two, that's good. I know Professor Wang has talked about the working scopes of offshore geotechnics, the site investigations, geohazard, and spudcan foundations in offshore engineering. Come on, I really like to have more than 1 response here, if you can. And I will ask a few questions during my talk. So I really just like you to practice that you can type in the chat. I'm sure you all can. You can probably type, faster than me. But I just want to make this session a little bit interactive rather than just me talking all the time. Okay, I've got another one. Constitutive model, effective stress, and pole pressure. Brilliant. Excellent. Oh, this is from the same person. So let me see, we have 37 on the screen. Besides me, besides the person who responded, we have 35 of you and have no response. Can we get a few more? Oh, are you really there, or you left the screen? Just turn it on and left. Or you can just, you know, type Y for yes, I have attended those sessions, or no, to tell me you did not attend those sessions and you are here today. No, okay, that's fine. Anyone else? Yes or no? I just want to have a sense of what you have learned, you may have learned the last few sessions, and maybe you're new here, that you're new to the series. Okay, so what can I do to make you a little bit more interactive rather than me talking here? Can I get a few yes or no? Got 2 no's here. Oh, good. So I got 1, 2, 3, 4 people. Can you give me a few? Few others that you haven't typed in anything? Okay, I got another one. 1, 2, 3, 4, 5, 5, 6. Okay. Okay, we got a few no here. That means you haven't attended the other sessions, but you're here today. Welcome. And so, okay, I'll get another no. Do we have anyone? I mean, the first 2 responses, talk about what they remembered. Definitely is a yes, that attended other sessions. I remember the CPTs, geohazard, spudcan foundations, site investigations and things. It looks like we only have 1 attended the other sessions. All the others are no. Is that correct? Has anyone attended? Just type yes, why, that if you have. But certainly the chat session is working, and I would like you to be more interactive, because if you are just turning the screen and left the screen and not listening, just, you probably don't need to do that. If you are interested and you're really welcome to stay. I will ask every now and then a few questions. I would like to see any responses. If you say, I really don't know how to answer, just say, I don't know. That's also okay, because I just, to do online talk is not easy. That if I don't know you are there, and whether you're listening. So I want to make this session, you can learn 1 or 2 things, and that you feel is not super valuable, but a little bit valuable, that we're not wasting, I'm not wasting your time. So so let me get started. Thanks for all the people responded in the chat. I'm just going to share my screen. Okay. Fine. Here's Can you see my screen? Yes, thank you. Thank you. Thank you very much. I got a few yeses. Yeah, wonderful. Wonderful. Okay, so now we're going to start. I did prepare a couple of topics. We'll see how long, how much we can get through. I think sometimes to get through less content to have more understanding is more useful than get a lot of content and nobody understands. Okay, so you can look at the title here, Decommissioning of Offshore Flexible Flow Lines to Torpedo Anchors. So if you have not, have any contact in decommissioning, and I hope you learn, one or two things from today's talk. So this is the last section about offshore geotechnics in the Global Ocean Open Courses organized by the Ocean University of China and the Academy of Future Ocean. I'd like to take this opportunity to thank the Ocean University of China and the Academy of Future Ocean to invite me to give this talk and to have an opportunity to meet you and to learn a few things together today. Okay. So this is a world map of the few quite large oil gas fields around the world. So you probably, I'll say you hear some of them or all of them. And so Gulf of Mexico, Brazil offshore, North Sea in Europe, Gulf of New Guinea, West Africa, and the NWS is northwest shelf of Australia, which is okay. So if you, I'm here, I'm in Perth of Western Australia, and the northwest shelf just the northern part of Western Australia. So Western Australia is a large state, the largest state in Australia, and has a lot of activities on the oil and gas industry. Just a quick question that around the world and nowadays, we know that the oil gas industry offshore started nearly 150 years ago, started from California. And then gradually they developed around the world. And there's a lots of oil gas platforms in operating today. I want you to have a quick guess to say how many, as today, how many oil gas rigs marked for operation at this time? So I'll give you a few choices. You can guess, or you can search online, whatever you have the resources on. So from 200, 400, 600, and 800, or maybe 1,000. So have a guess between these few numbers. What do you think? What do you feel? The oil gas rigs marked for operation today. Just send me anything. From 200 to 1,000, have a guess. If you know, just type it in. If you guess, just put your guess the number in. I just want to have a feel of the size of this industry around the world. 1,000. Yay, we got one. Anyone else? 800, 400, 420. Oh, that's accurate. Anyone else? If you agree with the 1,800, 400, or do you have a different number? Come on, give me a few. What do you think? So the reason we said marked for operation is, some of the oil field is still developing, some of the field has gone over its life. So when we say marked, we just say what is we think is in operation today. So thank you those who put in some numbers. I'm going to, I will remember these names that I'm hoping that to participate in the conversation throughout these 1.5 hours today. And I also really hope those have never said anything can do something that I'm sure if you difficult to type in anything that is not difficult to type in a number. So thank you for the guessing. So of course, I checked online, and is in nowadays is about 650 oil gas rigs marked for operation as it today. So you guys is not too far away from it. So that's the sheer size of the industry. They, if you look at this map, they are everywhere. Then you may ask a question to say, what about China? So we have Australia, we have Europe, we have America, we have Africa. What about China? So this is the data I get online to say when I say the oil gas offshore around the world has been developed over the last nearly 150 years, so more than 100 years. But Chinese oil gas industry really, you can see that started to the 1950s, and this data showed us that until 2013, and the vertical axis is how many millions of barrels per day, the production. So you can see the China's oil gas industry has been developing since the 1950s and really picking up after the 1970s. I also have a map here, is the China oil reserves. So in this map, you can see we have a lot of oil gas fields on shore, and the few fields offshore. So the onshore has been developed first, though we all know the Daqing field, Shengli field, and a few others as well. But if you look at the offshore fields, that's the field here. This map actually is the map of 2009. So it's not the very updated one. So if we look at the 2 YouTube videos to talk about China oil gas field development today. When I say today, it's 2025. So I'm going to use this one, and then I think I need to do something so you can hear the sound. I need to go to the share. And no, wait a minute. Did I stop the sharing? Are you still? Mm-hmm. Yeah. Okay, let me see here. Okay. Here, PC audio. Okay. Let's go. Let's watch the first one. It's coming. And it's loading. Can you hear?
Professor, I can hear you, but you just stopped the screen sharing.
I did? Oh, okay. Let me. So you can't see the screen?
Yeah, I can
Okay,
see.
let me stop. Okay, what happened? Resume sharing. Can you see my screen now?
Yes, sure.
Can you? Okay, yeah, I'll start again. Sorry, my bad. I want you to pay attention to
有了日期开发的经验，创新采用了深浅结合开发模式，让潜水拦网架平台与深水生产系统协同作业，既降低了成本，又提升了效率。
Pay attention here. The subsea structure. Okay, so that's one. Let me show you another one. So this is a Shanghai 1号, it's a gas field. And so what I want you to pay attention to, because we are working in the offshore geotechnics. So I want you to pay more attention on what is on the seabed that you can see.
In the South China Sea, the Liuhua oil field, China's first deep-water oil field cluster, has seen rapid oil and gas production during the country's 14th five-year plan from 2021 to 2025. Since it began operations in 1996, the cluster has produced 38 million tons of crude oil, accounting for more than 95% of China's total deep-sea oil production. Two standout engineering feats for the cluster are the Haiji-2 deepwater jacket platform. It's commissioned 27 production wells and can...
So pay attention here and look at these yellow lines. And that's the subsea structure, part of the subsea structure.
Achieve a daily crude output of around 3,400 tons. The second is the Haikui-1, a cylindrical FPSO facility, or floating production storage and offloading facility, that refines and stores the crude oil collected from Haiji-2. The FPSO is nearly as tall as a 30-story building and can accommodate full-time crews. Its builders say it can operate continuously at sea for 15 years before needing to redock. Both the Haikui-1 and Haiji-2 recently withstood typhoon-level wind gusts and were able to remain in operation.
Okay, ooh, this is something I need to stop.
Almost all of the machines that move around our planet
Okay, so now I would like you to see something here. So the first one is about Shanghai 1号, and the second one is is a gas field developed and start operating middle of this year. So it's off the coast of Hainan. The second video is Lihua oil field in the South China Sea. So what I want you to type in the chat is, have you heard of this? You know, if you heard of one of these or two of these, just say yes. If you say, oh, I've never heard of this, and just say no. So give me a few responses here. 深海1号 and 丽华 oil field, which is 海葵1号. Yes or no? Good. So we know the 深海1号. Said yes. Thank you. Anyone else? Yeah. Okay, so for all the other students here, I mean, you may not be students, you may be a researcher, you may, I really want you to, you know, if you are studying in this field, and you should pay attention to the development around you. Like of course, I pay a lot of attention to the Northwest Shelf oil gas development in Western Australia, and we have a lot of research projects, student design projects, based on those constructions. Okay, so you can see that even though we have this oil gas field marked in 2009, and through these two videos, we know that they are still developing today. So the development is still going. So you probably, if when I stopped in the middle of the video, that you have seen these subsea structures. So these yellow lines here, they are the flexible flow lines to transport the oil production from the well to the platform and to the onshore facilities. So what is the, this is made of? The offshore flexible flow lines. So this is a close-up of what is the inside and from inside to outside, the materials they use. The inside is the interlocking stainless steel, and then we have the plastic, and then we have the interlocking carbon steel, and this is the double cross wound tensile armors, and this is the plastic and the cover, or they call it the nylon. So we said currently there's about 650 oil gas rigs in operation today, and the development started more than 100 years ago. There are a lot of oil gas fields. They have reached the end of their life, like all the oil and gas productions have stopped. Then what we need to do is to decommission the field. The decommissioning, probably not in the, you know, for the oil gas field, they are started today, you know, the two videos I showed you today, they're going to be operated in the next few decades. But for the oil gas who developed earlier and they reached the design life, they need to be decommissioned, they need to be removed, and the production have stopped. Because in Australia, in the next 30 years, they will have thousands of kilometers of flexible flow lines need to be commissioned. And then I have a question here to say, I want to recycle it. Then you may ask the question to say, why can't we just leave it on the seabed? Why do we need to, take it out and then to recycle it? Can you think of any reason that they cannot be, and they better not be, left on the seabed when we move all the platforms away, when we stop the production? Any reason you can think about? If I say, from an environmental point of view, they are not allowed to be left on the seabed. What do you think could be the problem? Any single reason you think, yeah, because of this, and they are not allowed? So today's talk is really a look into the future. And you're probably doing a lot of projects on how to design a foundation, how to innovate a foundation. But this one is really in the future when the oil gas field reach their production life, and what we need to do to be environmentally responsible. Okay. Anything you can think about to say, yeah, you can move all the platform away, you can recycle those materials, but we can't leave these flexible flow lines on the seabed. Anyone? Okay, so maybe you have never really look at these aspects yet, because especially China's development is still, ahead on building the platforms, building the capabilities. So by regulation, these flow lines are not allowed to be left in the seabed. Because if you look at the production here, it must be a deep ocean construction here, because the floating platform and with the anchoring system here, and the platform for the drilling. Because nowadays, even the video I show you, the China development is Shenhai 1号, 海葵1号. They are deep sea structures. So the deep sea structures around the world has reached 3,000 meters, which is 3 kilometers in depth. So what is the scale of that? The scale of it is really like the tallest building in the world, the Burj Khalifa in Dubai. So we all know that that's the tallest building in the world. Do you know how tall is that building? Anyone? The Burj Khalifa, the tallest building, 800 meters. Yes, excellent. 828. Oh my God, that's so accurate. Thank you. So yes, the tallest building is reported as 828 meters. So it's just a little bit less than 1 kilometer, 1,000 meters. So if we have oil gas field built in the deep sea, 3,000 meters in water depth. So that's about 3 or 4 Burj Khalifa stack up. So just imagine there's a 4 Burj Khalifa step up, and that's the depth of the water that we explore those oil gas field. So it's very, very significant. Okay, so come back to the flow line. That we know that if we build anything in deep water subsea, we need it to be very, very good, strong, never break, because any stoppage of production one day of any oil field, they cost millions of dollars. So we don't want anything to be broken, because, you know, you say, oh yeah, when it's broken, we can fix it. You know, in that depth, fixing anything costs a lot of money. Stop, just forget about fixing anything, just stop one production day, and that's millions of dollars lost. Okay, so so these flow lines, because they are in the subsea structure, they are built to be deconstructible. They are built so strong and they will never be broken. I mean, that's the philosophy of the structure here. So that's why you can have the stainless steel, the nylon, and this, you know, double cross wound tensile armors, and the steel in here, and the nylon protection, and the protection layer here. It is so complex, it's so strong. That means we don't need to fix it. It will be, you know, in operation 30 years, 40 years, 50 years, and they will stay there to transport the fluid. And the reason that they are not to be left on the seabed because of the plastic here. And we know that the plastic in the ocean has become a big, huge environmental problem in the world, because there's a lot of plastic waste dumped in the ocean, and they affect the ocean animals' life and the ecosystems. And because of plastic, they just can't be degraded. So because there's a plastic in these flow lines, and they are not allowed to be left in the seabed. But there's in the regulation, there's one clause to say, because they are in deep water, if take them away from the seabed, take away from the seabed to onshore, if this one can damage the environment more than to leave it on the seabed, then we leave it. Okay, so you can see that there is still opportunity for the operations companies to say, yeah, we can leave it on the seabed. However, they said, if you leave it on spot, you have to bury them. And we know that if you know a little bit offshore construction, you know that to trench anything in the deep sea seabed and to bury the kilometers and kilometers and kilometers of flow lines is going to cost a lot of money. So, so the company has to think about it. If they really don't want to take them away from the seabed, they have to bury them below the seabed to reduce the effect on the environment, the damage on the marine environment. Okay, so basically, if you can't take it away, you have to take it away. Just for Australia alone, if, you know, in the next 30 years, we have thousands of kilometers of these flexible flow lines need to be decommissioned, and to recycle them becomes an issue. On top of that, just the sheer amount of flexible flow lines. The other thing is that they are built so strong. That means that they are very difficult to be destroyed, to be used for anything else. So because of this, the offshore company in Western Australia called Woodside, they have a department to look into the decommissioning of these flexible flow lines. So they had what they called brainstorming session in the university here. They gathered all the researchers from the different universities, research institutes, and together, and they talk about what problem they have. They said, we have these thousands of kilometers of flexible flow lines need to be commissioned in the next 30 years. And we want to, to know what are the options we have. We need to recycle them. Otherwise we have to dump them in the waste field. So if we can reuse them, reutilize them, if you look at this, they're all very good materials. They are good materials. And it'll be a big waste. We just dump them as waste. So during those brainstorm sessions, there are quite a few ideas. Somebody said, why can't we take these pipelines and reuse them in the dam reservoir when we need to release water from the reservoir to the downstream? So that is one of the ideas from the hydraulic group. The question is that because if they've been transporting oil productions, there may be harmful elements, left in the pipe. So the pipe needed to wash because the reservoir normally is the supply of drinking water of the region. So the what is the residue? The residual materials left in the pipe and can be a problem. Besides all other ideas, there's another idea from materials group. And they said they can freeze and heat the pipeline and completely destroy the structure. And you can get the metal out, you can get the plastic out, and the metal part can be reused for anything else. So that I feel this is a quite good idea, but also depends on how much energy you're going to spend. Because we're talking about circular economy, we're talking about sustainability. If we want to recycle materials, we have to spend a lot of energy to do it. We have to look at the carbon emission and the energy consumption, whether it is worthwhile. But I do think that is a good idea. So one of the ideas from my group is can we reuse these flexible flow lines to make a foundation material? And the one I suggested is torpedo anchor. Because we know that is a long cylinder, can we use that as, the main body of the torpedo anchor? And so, quick question here. Have you heard about torpedo anchor on the offshore foundations? This type, yes or no? Torpedo anchors. Anyone? Yes, lovely. Anyone else? Do you know what's torpedo anchor? No, you can say no, that's fine. There's no shame about, if you don't know anything. As a fact that when I was in the 20s, I thought I knew everything. Okay, I don't want to admit I don't know anything. So anything I say, I know everything, thank you. Someone say no, that's good. As I'm, getting older, I think the older I get, the more I know what I don't know. So I just feel there's so much things that I don't know. In the 20s, I thought I knew everything. So yeah, don't be shy if you don't know anything, that's fine. So we have 1 yes, 1 no, thank you. So my idea is to transform these flow lines to make a torpedo anchor to use for new construction. I mean, nowadays we talk a lot more about renewable energy, and for offshore, there's offshore wind turbines is one of them. You know, if this can be transformed to torpedo anchors that can be used for floating, maybe floating wind turbines. And the other renewable energy, what's the other renewable energy offshore, other than offshore wind turbines? What are the other forms of renewable energy offshore? Can you think about any besides offshore wind turbines? Besides offshore wind, what other energy we can harvest from the ocean? We're talking about the sustainability, sustainable energy options. Can you think of any? Besides offshore wind turbine? Wave energy, excellent, that's great. Yes, so we have wave energy devices, and it was a lot, there's a large wave energy research center in Western Australia, but it's not on the north side of Western Australia. That's the Northwest Shelf. There's a lot of oil gas field there. It's on the southern part of Western Australia, and they are building the wave energy devices. And because the wave energy devices depends on the floater in the water, and the waves make it up and down, and the floater has to be anchored to the seabed. So they need anchors. So the other thing is tidal energy. Some of the tidal, you know, the tide, you every day they have 2 tides. You have upper tide and lower tide. So yes, so we got the tide energy here. Thank you. Yes, so tidal energy devices need the anchor to, you know, secure them onto the seabed. So anchor is going to be used a lot for any floating devices. Some of the field in the ocean offshore here in Western Australia, the tide can be up to 10 meters. So that's a great potential to build tidal energy devices. So all these devices, as long as it's floating, doesn't matter if it's offshore wind or offshore wave energy or tidal energy, they all need anchors to secure those devices. So this is the suggestion from our group. And then, and the Woodside Energy, the company, they like the idea. So they very quickly, they gave us the funding to say, yeah, we'd like you to explore these options. And so today we're going to talk about what we did, what we found out, and this is a very initial step to look at the potentials to recycle the offshore flexible flow lines to torpedo anchors. Okay, so we have some students say, yes, we know what's torpedo anchors. We also have a no, that we don't know what is torpedo anchors. So torpedo anchors is an anchor that you don't need to, because, okay, so we'll probably talk a little bit about the drag anchor. So the traditional anchor that you threw the anchor to the seabed, and then you drag the anchor to certain distances, so the anchor will key in below the seabed and then give you the holding capacity. So that you need a vessel to take the anchor there, and then you throw it to the seabed, and then you need a vessel to drag the anchor to certain distance, sometimes 1 or 2 kilometers, to get the holding capacity. But the torpedo anchor is this one here. You have the vessel, you throw that through, through water into the seabed, and you can see that this has a shaft, the center part, and has fins on the top. The fins is to give the stability during the flying in from the surface of water to the seabed. And then they develop some energy, which is velocity when they reach the seabed, and they go into the soil. When they buried in soil, and they can build, putting out a capacity to hold any floating device. So from this one here, you can see that their operation is much simpler. So that's the advantage of the torpedo anchor. You don't have to drag kilometers and to get holding capacity. This one, you just find a location, you drop it in, you develop embedment depth, and then you have holding capacity straight away. So you can see immediately what's the advantage of this torpedo anchor. So this is a torpedo anchor that it is a prototype. It's used in the field already. So this one is about 13 meters tall. So we have a little person here as a reference. So, if this is 2 meters, that's 7 times of that person. Then we have the wall area, the dry weight, and the submerged weight. So you can see that is about 80 tons. So this structure is very simple, and that's about 80 tons in weight that you can throw into the seabed. But because the diameter of this flexible flow line is fixed, because we recycle this flexible flow line. So we have to use whatever the diameter we have that to build a torpedo anchor in this shape. So the anchor we could make, it will be 4.2 meters in height, which is 1/3 of this large torpedo anchor we found in the field. And you say, okay, this is so large, this is so small. Is that going to be useful? The thing is, the large anchor uses much more materials, and higher capacity. And the small ones, they'll have lower capacity, definitely, but we can have anchor groups. We may have 3 or 4 anchors to hold one spot. Or we can use these anchors to secure smaller structures like seabed pipelines or fishing equipment, fishing net. So there are a lot of applications they can be used, the small torpedo anchors. Okay, so what we need to do here? Firstly, we need to develop an anchor using the flexible flow line, which is the centerpiece. And we need to test whatever we want to develop that has stability in water. That when you throw the anchor from the top of the water to the bottom of the water, it's not going to be swing away. It's going to go down vertically. And that's the stability we need. And secondly, we need to test the anchor that can penetrate into soils to certain depth. We know that the deeper the water, the deeper the embedment depth, the higher the holding capacity. So the embedment depth is crucial for torpedo anchors. So we're going to build a model anchor using the flexible flow line as the centerpiece, the shaft, and to test its stability in water and to test the penetration and holding capacity in soil. So these are the 3 people I worked with, and Minghui Gao is the final year project students who did all the testing. And Scott Draper is the hydraulic guy, which is a professor in hydraulics. Now he's the head of department of civil engineering here. And Shizad is the geotechnical guy, which is a professor in geotechnical engineering and working in the School of Ocean and Earth. Okay, so I just want to acknowledge that Woodside support this project, and the UW has a seed program to promote the students to working on project directly linked to the industry problems. And O-Tube is the O-Tube technician Wei Liu, and she helped all the testing of stability in water. And Manuel is the manager of Centrifuge Center here, so who helped the centrifuge testing for this project. So O-Tube. So O-Tube is developed by this group and led by Professor Liam Chen. And behind them, this is the O-Tube facility. So this O-Tube facility is built the first in the world that developed in the University of Western Australia. It received a lot of industry awards for the innovation and development of this device. And the size of this device is that they have this is the motor propeller that it can generate waves. No, not really waves, it's the oscillatory flow along these 17.4 meters long testing sections. So they can generate a very large velocity, oscillatory velocity, to simulate the seabed flow. The section we used is just the middle section here, that we're going to drop the anchor from the top and with a 1 meter water depth. And we have a camera in front of the testing, and to record the dropping down the whole process to study the stability in water and the velocity that can develop when they reach the seabed. We know that the higher the velocity they can reach when they touch the seabed, the high energy they have to penetrate into the soil underneath. Okay, so this is the few models we developed. Remember the flexible flow line, they have a plastic cover on the surface. So, so there are 1, 2, 3, 4, 5, 6 models we built for stability testing in water. So this is actually a model that scaled down model of the real anchor. We called T98 torpedo anchor, just from the real anchor using in the field, and that scaled down. And the next one is the deep penetration anchor, which is the traditional one we showed you, with 80 tons in weight. So we scaled it down with 1 central shaft and 4 flat fins on top. Then these are the new anchors we developed. The first one is a 3R. So this one, the shaft is a shaft. These all the same shaft, but the fins, we thought we're going to use the torpedo anchor to cut it open to build these rings on top of the anchor. So we called 3-ring, which means the 3-ring as a fin. And this one is 4-ring, that there's 4 these rings on top as the fin. The next one, this one, you can see this yellow cover here. And what we did on the cover you can see here. So we cut this like a half moon shape to make it like the fish scale. So because we know that the fish, they can swim forwards, they can't go backwards because the scale can only have one directional easy swim. So we want to cut this half moon shaped, we call it serration, to simulate the fish scale. So what we want is really like if this one, they can penetrate into the soil easily, but when you put it out, these scales can provide higher capacity. So it's one direction is easy, so the penetration is easy and the come out is difficult. And that's exactly what we want. We want the high capacity. To test the fish scale, we have a large fish scale, we call the large serration, and this is small fish scale. So the size of the serration is smaller. So we want to test which one is more efficient. And the top, the fin is the same as this deep penetration anchor. So the fins are the same. We only want to test the effectiveness of the serration here. So if I name this 1, 2, 3, 4, 5, 6. So I want you to have a guess. After all my our stability in water test, I want you to guess this 3 ring and 4 ring, which one is better? And this large fish scale, large serration and small serration, which one is better? So let's count again. So, okay, so 1, 2, 3, 4. Can you guess 1 and 2, which one is better? And 3 and 4, which one is better? Have a guess and let me know. 1, 3. Four wings, 3. 4 ring, yeah. 4 ring is 2, 3. 2, 3, okay. 4 ring, yes. I guess that, yeah. Any guessing? Have a guess. You're not going to be marked. You're going to lose anything. Just have a guess. Have fun. 1, 3. So it's 3 ring, large scale, large serration. Come on, give me one more guys, so we can move on. One more, anyone else? Come on, 1, 3. Thank you. Okay, remember what you guessed. So 1 is 3 ring, 3, nearly everyone guessed 3 is the large serration. Remember that. Let's see if your guess is correct. Okay, the stability in water test. So this is the at the bottom of this test session. See, this is 1 meter water depth, and we drop the anchor, the model anchor from top, and we film. We take a video of this is coming down, and we analyze the video, we get velocity, distance, stability. So the stability is that we aim at the center of this ring. So this is the ring here. So we have 3 rings. We have 360 millimeter, and then we have 1. So you can see this second ring, can't see here. The second ring is 104 millimeter, and there's a center part is a 45 millimeter. So we really want for an anchor that can have a stability in water, they will hit the center of this ring. So we film the dropping process, and we measure when they touch down on the seabed, how much distance of this anchor away from the center. So we're going to analyze its stability. So this is measuring data. So this blue line, so this horizontal axis is time. That's the recording time. So we have the vertical displacement, and when they reach the seabed, the displacement is stopped. So the vertical displacement has reached 1.3 meters. And then this red line is the vertical velocity. So using the videos we took and we analyzed the data, the velocity is increasing, which is great. And then they reach this value, which is 1.3 meter per second, and it's not increasing anymore. So you can see that when the anchor reached 1.2 meters, so you can see that the velocity is increasing. When they reach the 1.2 meters, they start to stabilize. So this one we call the terminal velocity. So the terminal velocity, let's say when you have a deeper, even the water is deeper, the velocity is not going to increase. So this is the velocity we want to know, that which anchor can give us higher terminal velocity. Because the higher terminal velocity, the high energy that the anchor can penetrate into soil. So this is the, we use the terminal velocity to calculate the CD. We know that if you, in your fluid mechanics, you know that the F equals to MA, that the need to take away the drag force. The F should be the gravity take away the drag force. The drag force depends on the drag coefficient. So the higher the drag coefficient, the slower the terminal velocity. So this is the T98, and we know this is a long anchor, so the drag coefficient is quite high. And then this is the DP, the deep penetrating anchor, which is as a reference point. And then we have this 3R, 3 ring, and 4 ring. So 3 ring is number 1, and the 4 ring is number 2. So to think about which one you guessed. So the number 1, 3 ring give you lower drag coefficient. And for the large serration, small serration, this is number 3, this is number 4. So the number 4, the small serration, give lower drag coefficient. So from the water stability test, number 1 and number 4 are better. So this is only one data, drag coefficient. We're also going to measure the distance from the center, which is the stability, because we don't want the anchor to swing to one side. Because when the anchor reaches the soil surface, and the angle has to be controlled. They cannot be larger than 3 degrees. So when they swing, they will generate a large angle when they reach the surface. So this is the T98. This is the reference point. And let's look at the 3R and 4R. The shorter the distance from the center, the better, the more stability. So the 3R and the 4R, the number 1 is better. The 3R is better. And the large serration and small serration. The large serration give a very large variation of where they can drop in, and the small serration is closer to the center and less variation. Again, number 1 and number 4, 3 ring on the fin, small serration on the shaft is better. Okay, so from the stability test, these are the 2 we're going to choose because they are performing better than the other. I think some of you guessed right. You guessed 1, but I haven't seen anybody guessed 4. So to be honest, before the testing, all of us in our testing team think 3 would be better, but it didn't. There might be all different reasons for that, but that's the testing results we have. Yeah, so we're going to choose these 2 for the next stage of testing, which is we've done the stability in water. Now we're going to look at the penetration and holding capacity in soil. We did the test in the centrifuge, and centrifuge, we have this National Geotechnical Centrifuge facility in EWA, and this is, we claim the only centrifuge in Southern Hemisphere. I know there's a lot of centrifuges in China. This is only one in Southern Hemisphere, but I did hear that there's another one built already. I'm not quite sure whether it's in operation in Southern Hemisphere. So this is, we call it a small beam, and this is a large beam just built not long ago. This is the first one we built. And this is the drum centrifuge that you can generate waves and things. And this is the second one built. This is the last one built with the large arms. And this is the Professor Mark Randolph, who is the one came from UK, who did undergrad in Oxford and PhD in Cambridge, and then after PhD, he came here to build the geomechanics group, now the Center for Offshore Foundations. So he built the first centrifuge because Cambridge was the the pioneers for centrifuge testing in geotechnics. And this is our centrifuge team. Christoph now is the director of the Ocean Institute, and Conrad is the director of this centrifuge facility. Mark Cassidy used to be the director of the Center for Offshore Foundations. Now he's the, I think is PVC or DVC Pro Vice Chancellor in Melbourne University. Okay, now remember we choose the 3 ring, and we choose the small fish scale for the shaft and 3 ring for the fins. So what do we have? We have 4 models. So this is the base model, which is the reference point, a deep penetrating anchor with the normal shaft, 4 fins. And so then we can have this fish scale with 3 ring. And then we have the fish scale with normal fin and normal shaft with 3 ring. So this is 4 models. Basically, we have just 2 fins and 2 shafts, and there's a screw in between. So they can swap their fins, make another 2 models. So we tested these 4 models. Besides this reference one with a deep penetrating anchor, so we have number B, C, and D. So C is the fish scale with 3 rings. So there's the shaft and the fin both are modified. We call it hybrid. And C is we just do the modification of the shaft with a fish scale. We got a fish scale anchor. And this one we called deep penetration anchor with a 3-ring. We call it 3-ring. So I wanted to look at this hybrid, fish ring, and 3R. Which one do you think they will perform the best for penetration and holding capacity in soil? Have a guess. B, C, and D. What do you think? What do you think? What do you hope that perform the best? Anyone? A, B, C. B, B, C. Okay. So B is this hybrid, C is this new fish anchor. So this is a centrifuge. I'm not going to talk about too much. I'm aware of the time here. So I do want to talk about this guide, that because the centrifuge is spinning around, so the gravity is in the radial direction. So without the guide, the anchor will just swing. So we need this guide to make sure the anchor can drop down to, this is the seabed, which is the testing soil, is clay. We're testing in clay. And the purpose is to measure the velocity when they pass in this. We have a 7 measurement here. It's a photo emission and reception pairs to measure the anchor velocity before they get into the soil. And so this is what it looks like when they pull out. Okay, so this is the T-bar testing to test the soil strength. So if you look at the undrained shear strength here, all the T-bars give us average about 8 kilopascal. And we did a group of cyclic loading test. Does anyone know why we do cyclic loading tests in clay for T-bar when we test the soil strength? What we are testing? Any idea? Anyone? Come on. Residual strength, yes. Wonderful. Yes. So when you penetrate the T-bar and you pull it out, and if you do cyclic, you can see this is the first cycle, and this is the last cycle. You can see the strength, the initial strength, and the end strength is different. So we can know after many cycles what is the residual strength, which is also the soil sensitivity. So the initial strength over the residual strength give us the soil sensitivity. And a lot of marine clays will have a sensitivity larger than 1. So this is the sensitivity that initial strength over the residual strength. So if we look at all the tests we've done, it's a range from 3.2 to 4. So we normally use a 3.5 in our analysis. And this is the anchor dropping height. So the dropping height is about 9.3 meters. This is a prototype after 50G testing in the centrifuge. And then we measure the velocity. This circles is the 7 perps, measure the velocity. And then we use this formula to get the coefficient mu, which is the related to friction, but it's not a pure friction coefficient. But we use this one, and then we use this formula to measure what is the mu, what is the friction effect on the anchor when they penetrate into the clay. So when we use mu equal to 0.88, so the prediction gives a very good fit. So we get this number here. So this graph look at the impact velocity. So we know that the higher the impact velocity, the more energy we have the anchor into the soil. And on this one, the top is the dropping height. So the dropping height, we changed the dropping height to 3 levels. And then, so the dropping height here is over the length of the anchor. So the length of the anchor for all the anchors we're testing are the same. So this is 4 times, 3 times, 2 times the anchor length we drop. And then we look at the penetration embedment depth is also normalized by the anchor length as well. So it's around 2 times the anchor length. So we kind of see that the higher the dropping height, the more penetration depth that we have here. And if you look at the 3R, the cross, that give us higher penetration depth. They're all better than this reference one. The reference one is a deep penetrating anchor with no modification. And the diamond here, the diamond is a hybrid. So the hybrid is not bad. And the fish scale is a triangle. So the triangle one seems not better than the deep penetrating anchor. So with the embedment, we're going to look at the different groups. So this star is a 3R. So this is the total energy, the kinetic energy and the potential energy. When we put the energy together, and you can see the trend here, the higher the energy and the deeper the embedment, which makes sense. And through all the different ones, the 3 ring seems to give us a higher embedment depth. And all the others are quite similar to the unmodified anchor, which is the circle here. And this is the holding capacity. Normally, of course, we think that the deeper the embedment, the higher the holding capacity. But when we look at this one here, the holding capacity of these 3 ring, we know the 3 ring penetrate deeper compared to those ones. It's because this is the embedment and this is the capacity. We would think that the deeper the capacity, the deeper the embedment should have higher capacity, but this one gives us slightly lower capacity, and this one gives us a slightly higher capacity. Then in this number here, this is the first number is the sequence we did test. This is the first anchor. This is the fifth anchor we drop in. This is the second one. And the second number is what I need to pay attention to is the consolidation time in days. So after the anchor dropped in, how long do we wait before we put it out? But we know that in the field, the anchor will be dropped in and we may wait for months before we hook it on to any floating facility. So the 22 days, 28 days really probably won't tell the consolidation effect on this one. So this one we would see as the reason for the 3 ring and the hybrid that has lower capacity could be because remember the soil has a sensitivity of 3.5 and the soil is more disturbed by the 3 ring fin. And the normal fin will have less disturbance of soil. The soil strength may stay higher. Okay. So what conclusion we have? From From the O-tube testing, we find the number 1 and number 4, which is the 3-ring and small fish scale, will have stability in water. And from the centrifuge testing, we found the normal fin performs better than the 3-ring fin, and because the disturbance. And the more testing we need to do to look at after consolidation, after the soil recovered its strength, if that's still the case. At the moment, with short-term putting out capacity is the fish scale with the normal fin, but not the 3-ring fin. Okay, so I think B and C. So a lot of people get the C. I mean, some people get C, and that's good guess with their normal fin and has a higher holding capacity. Okay, I think I have reached nearly 10:30 the time. I did prepare something else, but I don't think I have time to talk about it. But I'm so happy that we have some interaction today. Although I know some of you have never responded, but I thank all of you to be here. I'm happy to answer any questions you have. You can type, you can talk. That's all good. Anyone? You can ask your question. You can type your question. That's all for today. I finish my talking, and it's your turn to talk or type. Okay. Looks like you don't have any questions. Maybe just say or type. Is there anything that you learned today, or anything useful, or whatever? Whatever you want to say. Anything? How should we consider the impact of sediment grain size? Do you mean in centrifuge testing? Are you talking about centrifuge testing and they scale up the grain size? Or do you mean that, yes, okay. Yeah, so the question is how should we consider the impact of sediment grain size in centrifuge testing? Remember that if you spin the centrifuge in 100 G, any size, the model size, the foundation size, is all pumped up by 100 times. So if you have a 100 millimeter foundation, and then you test the real size prototype foundation 10 meters. Then there is a question that been asked quite constantly and quite commonly, that the soil is still the same size, right? When you spin in the centrifuge, the particle size has been pumped up by 100 times, which is not the real soil particle size, which is true. However, we see the soil as a continuum material. We look at the mechanical performance, which is the strength of the soil, the permeability of the soil, the consolidation of the soil. So we look at these characteristics. If these characteristics, they can resemble the field material, and we think that's good. So so for the particle size, we're not considering each individual particle. We consider the particle, the overall performance of the particles together. However, by saying that, for clay, it's nearly never a problem, but for sand, it may cause a problem when the foundations or anything you want to test has a smaller size. And if the particle size, if the foundation size is, it has to be more than at least 10 times of the particle size. So if the foundation you're testing, you scale down, it becomes so small that less than 10 times of the particle size in sand, and then maybe there will be a problem because the particle size will affect the interaction, the performance, the testing results. Anything else? How to transform the retired flowline material stuff into anchor or other something refers to your group's new idea. Okay, so basically you just cut a section. Let's say I want to build an anchor because the diameter of the flow lines will be around a meter or less, let's say half meter. And then we can cut like a 4 meter section. And we do need to make a cone tip. And then we need to add phenol. But we do think because this, but in the middle, we may drop in any waste materials, like any crushed materials we can put in the middle, may make the anchor heavier. Then the things about the fish scale we want to cut, because we have this yellow plastic cover of the flexible flow line, and we think that's possible, we can just machine cut the cover of the plastic to make the fish scale in that sense. Yes, I like this question because this is the first ever study on this and is nothing close to the construction stage yet. There is a lot of details we need to think about how to make a fin stay you know, on the surface, and how to make a cone tip, how to attach the mooring line to the top of the anchor. So all these details need to be considered whenever they can be closer to the construction stage. Very good question. It's so environmental friendly. Thank you. I think that's what we want to achieve. You know, all the development on the wave energy, offshore wind turbines, all these sustainable energy development is trying to reduce carbon emissions, and all the waste recycling. Yeah, is to make the less waste to the to dump into the waste ground and to reuse them. So they're talking about the circular economy is a recycle, reuse, recycle, to have a full circle of it. So I think for all of us, especially for you, younger generation, really need to look into this. Whatever we produce, And whatever we make today, we have to think, end of their life, can we reuse them? Can that be recycled? If not, would that be a good idea to do? So, because it's my future, it's more your future as well. Thank you. Okay. Thank you very much, everyone, for stay on. I'm just going to stop sharing. Okay.
Thank you, Professor Hu, for your inspiring lecture, and I guess they may have learned a lot, and it will benefit them for their.
So.
Yeah.
Thank you so much. Thank you for organizing everything, Xuanying. And also, I'm checking the attendance was 38 before, and it's 35 now, and which is great. Thank you very much for staying on. And if you have any questions, if you want any, we have actually published this this testing on the journal paper. If you wanted to read the journal paper, let me know. If you want to know anything, just let me know. Yeah. Thank you very much. Have a nice day.
Thank you, Professor Hu, and have a nice day too.
Okay. Bye-bye, everyone. Thank you all.
Bye.
Bye-bye.